And recently, the weather is so great. The sky is brilliant. But we need to study. Even though the weather is good or bad, we have some plans, study schedule. So actually, so for this course, so we need to take total of 30 classes. So that's the mandatory from the government. So we can skip the classes. Okay. So let's enjoy some joy of running. So in the previous class, we learned about the control hazard by branch instructions. And then I explained that if the branch is determined in memory stage, when the branch instruction is in the memory stage, the result of the branch instruction is determined. And then based on the result of this branch instruction, the PC, the next PC value is updated. And then this next PC value is reflected to the current PC value when the branch instruction is in the write back stage. So, which means that when the branch is taken, so I said, if the branch is taken, the instructions in these three stages, in ID, execution, and memory stages, are incorrect. So that those instructions are wrong instructions, so we need to flush. The flush means flush out. So we need to flush these instructions. So that means if a branch is taken, then the condition of the branch instruction is true, and we need to waste 3 cycles. And then in order to reduce these wasted cycles, we move the determination of the branch instruction in the ID stage, right? So in the previous class, I explained about the new data hazard by this enhanced branch instruction, not branch instruction, enhanced branch implementation. Okay? The instruction is the same, but implementation is changing to reduce the control hazard by branch instructions. Okay, so I was explaining that I prefer this architecture really because the branch is determined at the existing forwarding unit. Okay, so and then I explained that we will have a lab assignment. So and then for the lab assignment, the last lab assignment, you will be requested to design pipeline architecture. A very simple pipeline architecture. So, and then I assume that the branch unit is implemented like this figure. So which means the branch is determined in EX stage and then after the forwarding unit. Okay. And then also I explain about some techniques that can reduce the control hazard by branch instruction. It's a prediction techniques. So actually, our normal processors rely on these prediction techniques. So I explained that if the prediction hit rate, so if the prediction hit rate means that the probability of the prediction is right. So if the prediction hit rate is very high, then we can apply prediction techniques, and then with these prediction techniques, then we can improve the performance of the processes. Okay, it's a very good technology or architectural technology. Okay, so now, also in the previous class, I briefly mentioned the exceptions. The exceptions is just like terminology, name of this terminology, exception is just like the really exception. It's a very rare events in a computer processor. And then these rare events include the real exceptions, like the divided by zero or on decoding error in the instruction, something like that. So these are also kind of exceptions. Also, the kind of some kind of exceptions include the interrupts. So like the typing keyboard, moving mice, also touching touch screen. Those events are generated by input and output devices like keyboard, mice, touch screens. So we can think that these events are very fast, frequent, and fast. But to the computer processor, so the clock frequency of the normal computer processor is around 3 to 4 gigahertz. It's very fast. And then compared to these clock cycles of clock frequency of the computer processor, our human events, the events from the input and output devices, are very slow and rare. So if exceptions or interrupts are detected by hardware, but hardware just detect the exceptions or interrupts and then return the codes of exceptions or interrupts to the software, like the operating system. And operating system has various kinds of exception handlers. Those are software codes. Okay, so exception occurs in a processor, and the computer hardware, the processor, just detect the codes of exceptions, and then the processor returns these codes of exceptions to the operating system, and then the operating system decides the PC, the program counter of the exception handler. Then the processor jumps to the program counter of these target exception handlers, and then instructions are fetched to the processor, and then the code and the exception handlers are executed. So I explain how exceptions are detected and handled in the processor, which means that the hardware also supports the detection of the exceptions and then so handling of the exceptions. So let's see how we can how a processor can handle exceptions. So then so I also explain some additional behavior of exceptions. So think like this. So you can say that this is it's a program counter like 04, 08, 0C, 10, and blah blah blah. But we can find many instructions like that, multiply, divide, and instruction, something like that. So when exception happens at a certain instruction, then processor need to store where the exception happens in a code. So which means that, so we can say that our exception, so divided by zero, like the kind of exception can occur in this if instruction, the divide instruction. So in this case, the processor needs to point the location of the exceptions in a code, which means that the processor needs to return the location. What is the location? It's a program counter. So processor needs to return the program counter of the instruction that causes exceptions. Okay. So we need to store the SEPC, it's a supervisor exception program counter. So which means that the program counter of instruction that causes exception is stored in the SCPC. And then, so let us assume that the exception occurs at this instruction, at give instruction. Then, what should we do? So, exception happened at this instruction. So, which means that these instructions are normal instruction. So, these instruction is deep instruction is some kind of how can I say? So it's a kind of abnormal or uncommon instructions. But the instructions before this deep instruction is the common instructions or normal instructions. So which means that the processor needs to complete the execution of these instructions, which means that the instructions before the abnormal instruction, like the exception that causes the instructions that causes exceptions. Then exception happens at this instruction. So the processor needs to return the location of the exception at the program counter, and execution of this instruction should be cancelled because this instruction is the abnormal instruction. Okay. Also, in a pipeline architecture, we can say that the following instruction methods and the instruction can be fetched in the processor, which means that the following instructions can exist in a processor. Then what should we do? So these instructions are cancelled, so which means it's flushed out in a processor. How about these instructions? So we already know that in a processor, the instructions are executed sequentially. So which means that if this instruction is incorrect or abnormal instruction, then the execution of the following instruction can be also uncommon or abnormal or some incorrect executions. Right. So which means that we need to also cancel all following instructions in a processor. Okay, so I explained that instructions. So we can distinguish instructions like the instruction before the abnormal instruction, these instructions, and then the instruction that causes exceptions. So we can say that there are following instructions at the instruction that causes exceptions. So the processor needs to complete execution of these instructions. So which means that a processor needs to complete write-back stages of these instructions. Okay. How about this instruction? The exception is detected for this instruction, and then processor needs to cancel the execution of this instruction, and then the exception handler should be called by a processor. Okay? The program counter is changed to the program counter of the exception handler. And how the following instructions? If the following instructions are already fetched in the processor, following instructions are also flushed. That's how exceptions are handled in the processor. So in order to return the location of the exception, the RISC-V has the SCPC register. And so this SCPC has stores the program counter of instruction that causes exceptions. Okay. Also, we need to return the causes of exceptions. So these causes of exceptions are also stored in the S code. Okay. So these causes of exceptions are also returned to the operating system. Okay. And then let us see that So we need to jump to the exception handler, which has the address of 1C0900. Okay. So so this is the example of the exception in a pipeline. So let us assume that exception occurs at this instruction at x1, x2, x1 in EX stage. Okay? So we can say that this is the example, just the example. So this is at x1, x2, x1. So and then as I said, there can be some previous instructions like sub, load. So if this add instruction is in the EX stage, and then we can say that there are already two instructions, idle stage and instruction fetch stage, like the other instruction, like multiplier or dig. So exception is detected when an add instruction is in the EX stage. So this is just an example. So, and then we already know that if this instruction is executed, then the result of this instruction is written to the register file. And then I explained that if an exception is detected at a certain instruction, the execution of this instruction should be cancelled. So we need to prevent exception from being written to the register file. And then, as I mentioned, we need to complete the previous instructions, like the sub and load instruction. Then we need to flush following instructions. So these behaviors should be supported by pipeline processor. So this is the additional hardware implementation that supports the exception handling in a pipeline processor. So like the branch instruction. So when the branch is taken, the already fetched instructions to be flushed. So it's also same to the exception handling in a pipeline processor. If the exception is detected, then following instructions will be flushed. So we can implement this flushing logic at the branch instruction. Also, we need to cancel some instructions that causes exceptions. Okay, we need to cancel. So in order to cancel the instructions that we already learned, that we can change all control signals of this instruction as zeros, right? So if the pipeline is stored like in the idle stage, then which means that the pipeline generate no instruction, no operation. And then in order to generate the no instruction in our pipelines, then we can make the all control signals zeros, right? And it's the same to the exception handling. So we assume that the exception is detected when an add instruction is in the EX stage, so which means that we need to make this add instruction not. Okay. So, and then in order to make generate no instruction, we can make all control signals zeros. Okay. Also, the SCPC and then as COSE, there are SCPC and then as COSE registers in pipeline architecture, and then these registers are returned to the operating. So it's read by operating system, and operating system decides how to handle the exceptions. Okay. So this is the example, and then this is the program counter of the exception handling. It's a kind of example, okay? And then let us assume the exception is exception occurs at this instruction. Okay. So when the add instruction is in the EX stage, then exception is deducted, and then you can say that. So in this example, if the add instruction is in the EX stage, so we already know the previous instructions like AND or instructions already are in the memory and write back stage. So we already know that some instructions or load instructions are in the write stages and instruction fetch stage respectively. So it looks like this, and the exception is detected. So when the exception is detected in the EX stage, we need to complete the execution of OR and AND instructions. And then we need to cancel these instructions. And so this is the program counter of the exception handler. And then as the exception is detected, then the code in the exception handler should be executed by a processor, which means that we need to jump to this instruction. So program counter is changed to the 1C09000. Okay. So this is the so when the add instruction is in the EX stage, the exception is detected. Then at the one cycle, okay, at the one cycle. So as I explained, add instruction is also flushed. So we need to cancel the execution of the add instruction, sub instruction, and load instruction. So you can say that you can see that there are bubbles here in the IO stages, EX stages, and memory stages. And then the OR instruction is in the write back stage. So OR instructions is kept in the processor. Okay. So the AND instruction is already in the write back stage. So the execution of this AND instruction is completed. And then at the one cycle, the OR instruction is in the write back stage. So which means that the OR instruction is also completed. And then this is the SD instruction, the store instruction. So you can find that the first instruction of the exception handler code is the store instruction, which means that the PC is changed to the first line of the exception handler, and then the store instruction is fetched. Okay, that's how exception is handled by a processor. So exception handling is very similar to the taken branch, right? And the branch is taken, then the program counter is changed to the target of the branch instruction. And then also when the branch is determined, following instructions are flushed. But even though the branch is taken, the previous instructions should be executed. It's actually same. The only difference is we need to store the program count of the instruction that causes exceptions, and we need to store the causes of exceptions. So these PC and then causes of exceptions are stored in the SCPC and SCOSE, right? And this is the only difference in exception handling in a processor. Okay. Okay. Then let's think about the multiple exceptions. So what are multiple exceptions? It's like this. So add, sub, load, the multiply. So for example, exception can be detected at sub instruction, and then also the exception can be detected at div instruction like this. And then let us assume that the exception of the sub instruction is okay. is changed. The exception can be detected at load instruction, and the exception also a different kind of exception can be detected at DB instruction. And then, so let us assume that this exception of the load instruction is detected when a load instruction is in the memory stage. But the exception of DB instruction is detected when this instruction is in the ID stage. Close the door. The question is how? All right, I did not close the door. Okay, so what happened? So if we see the pipeline of this processor, so like the D is here in the ID stage, and then multiplies is here, and then load is here, and then solve is here, and then add is here. What's the problem? And the exception is detected. So exception of this DV instruction is detected when the DV is in the ID stage. But if you see the load instruction here, load instruction is in the EX stage. And then let us assume that the exception of this load instruction is detected when a load instruction is in the memory stage. What happened? The exception of the DV instruction is detected earlier than load instruction. So what should we do in this case? I already explained how exceptions are handled in a processor. Okay, and then first, the exception is detected when a DV is in the ID stage. So what should we do? We need to cancel or multiply here, and then these instructions should be maintained. Okay, so it's the same to the previous example. Also, div is cancelled, and then SCPC and then SCOSE are stored for the div instruction. And then, so in the next cycle, this is done. Nope. And then there can be some instructions from the exception handler. And then the div instruction is cancelled or becomes the no. Load instruction is here, and oops. Solve instruction is in the write back stage. And then, and the load instruction is in the memory stage. Exception is also detected. What should we do? Exception handler is here for the div instruction. And then exception is detected for load instruction, and a load instruction is in the memory stage. So in the timing, so if we just consider the timing of these exceptions, exception of this div instruction is detected earlier than the load instruction. But if we just consider the order of instructions in our code, so we assume that actually the software assumes that every instruction is executed atomically. So which means that in one cycle, the add instruction is executed, and then the result of the add instruction is reflected to the processor and done. The sub instruction is executed, and then the result of the sub instruction is reflected to the processor. Done like this. It's atomically. How about this case? To the software side, exception of this load instruction is earlier than the exception of div instruction, even though the exception of div instruction is detected in the hardware earlier. You understand? So in this case, the exception of the load instruction should be handled first. Okay? Which means that, oh, load instruction is here, exception is detected, cancelled, and then exception handler for this load instruction is newly fetched. So which means that the fetched exception handler in the instruction fetch stage should be also flushed. Do you understand? And so after one cycle, this looks like this. So no, and the serve instruction is executed and then completed. So no is here, no is here, no is here, and then some code from no exception handler for load instruction will be here. So what I want to say is that the order of exception should be order of instructions. So which means that even though in a processor, exception of the late instruction is detected earlier, that can be possible, okay? Like this case. But the processor needs to handle the exception of the former instructions first, and then, so the exception is handled by exception handler. So what should we do? We return to this load instruction. But in this case, the exception is already handled, so load instruction can be executed. So which means that when the load instruction is here, so these codes are also re-executed. So it's fetched again in the processor, and then which means that the div is here, more will be here. And the exception will be detected again. So exception is handled for this div instruction again. Okay, so it's fetched again, and then will be executed by a processor. So you need to remember that processor needs to support the order of exceptions, like the sort table. Okay, so I want to say that so the order of exceptions should be the same to the order of instructions. Okay. And then this kind of exception handling is called actually precise exceptions. Okay, so which means that a processor needs to support precise exceptions. But some processors cannot support precise exceptions actually. But so usually we assume that a processor can support a precise exception. Okay. Sometimes a processor can support imprecise exceptions. So in this case, so actually we are learning about the very simple pipeline architecture, but actually in a real hardware, in a real processor, the architecture of the pipelining is very, very complex. Okay, so which means that actually the modern processors, like most of the modern processors such as the x86, desktop or laptop processors, also some ARM processors in our smartphones. So the performance of the modern smartphone is very high, right? So it means that actually in the 5-stage pipeline, we cannot support these high performances. Okay, so actually the modern processors have a very complex pipelining architecture, like the out-of-order processing, which means that the order of processing is out of order. So we are learning about the pipelining architecture like this. And then actually this pipelining architecture is called static pipelining, which means that the instructions are executed in order, not out of order. So which means that these instructions are executed sequentially. Right. The execution order is in order. But modern processors support hourable order processing, so which means that it's not easy to support precise exceptions. So some processors support imprecise exceptions. So in this case, the software needs to have the handling of the exceptions. Like, so the software just estimate the location of exceptions in the code based on some hardware reports. And then the software just codes exception handlers. Okay. But usually our processors support precise exceptions. It's not easy actually. It's not easy, but so it's a kind of a hardware specification. So we expect that a processor can support precise exceptions. Okay. Then, so please remember how the exceptions are handled in a processor. So just remember that the exceptions should be handled in the order of instructions, not the order of timing of detection. Okay. Then this is the precise exceptions. Okay, it's done. And then I will please explain about some real hardware. So actually we learned about the very simple 5-stage pipeline architecture of the RISC-V processor. But as I mentioned, the real processor, actually the architecture of the real processor is very, very complex. And so let's see some example of the process architecture. Actually, if you take the advanced course of the computer architecture, so usually these advanced course of the computer architecture is provided in graduate level, advanced computer architecture. Or so I plan to provide some advanced course for the senior students. Okay? But currently, our department just provide the advanced computer architecture course for graduate students. Okay, so which means that, so as I mentioned, so even though we learned about the 5-stage pipeline architecture, this pipeline architecture is very, very simple. So we cannot use this architecture. Okay, which means that the performance is very, very low. So let's see some example of the modern architecture. So actually, so I also posted this slide, so like instruction level parallelism, but I will not cover the content in this slide because this is the advanced sub-level. So I will not cover the content in this slide, but I will just show some example of advanced architecture. So actually, the modern processor, the architecture of the modern processors look like this. So the instruction interface. So it's the same to the some five steps of how instructions are executed. Instruction to text, instruction to decoded, and then instruction is issued to some different execution units, and then instructions are executed, and it's written back to the register file. But this is out of the execution of the instructions are out of order. Okay, so it's not easy. So this is the advanced level. So I will skip here, and here. So if you see that this slide, so you can find that so this is some year of the processor, and then clock rate, the clock frequency, and then pipeline stages, and issue list. So it means that how many instructions are fetched in cycle, and then out of the speculation, and then how the number of cores, and then power consumption. So if you see that this table, so you can find the so just 84, 86 is computer. It's out in 1989. So you can find number of the pipeline stages is just 5. So if you see the Pentium processor, it's just so much. So we can find both. So number of stages are also number of stages is 5. So you can find that if you read this, it's just 2. So which means that Pentium can execute 2 instructions per cycle. But in this course, we learned about some pipeline architecture that can execute 1 instruction per cycle. Okay, so you can find that the out-of-order processing is not supported. How about the Pentium Pro? It was introduced in 1997. Stage 10 is there are most pipeline stages. If you read this is just 3. Okay. Out of the processing or speculation is yes, it's supported. So you can find in 1997 the architecture of this processor is already different from the simple pipeline processor we learned in this course. Then the core architecture is the modern Intel architecture. The pipeline stage is about 14. So issue with is 4, which means the 4 instructions are executed per cycle. Then so yes, also yes for the out-of-order processing and speculation. Course 2, it's multi-core architecture. In chapter 1, I explained why we need multi-core architectures because of power. Okay, so the process architecture has been changing year and year. So also recently we encounter some also the changes in the process architecture. Okay. Okay, so this is the ARM Cortex A53 pipeline architecture. So actually, the ARM Cortex A53 is the in of the processor. So which means that the instructions are executed in order. But the architecture of this ARM Cortex A53 is also different. So the architecture is not same as the 5-stage pipeline we learned in the first. Even though this processor is the the processor, the completion order is different. Okay, but I will explain. So architecture is more complex. Okay, it is because we require fast, so high performance processor, which means high performance processor requires more complex architecture. Okay. So this is the simple diagram of the Intel Core i7 processor. So the Intel processor is more complex than the previous the processors. So okay, because the Intel Core i7 supports the out-of-order processing and then speculation and some other architectural techniques to improve the performance. Okay, but if you are interested, then you can pick the more advanced course in the computer architecture. The performance is so this is the performance of ARM Cortex A53, and then so this is the ideal performance. So which means that actually the ARM Cortex A53 execute the 2 instructions per cycle, which means the CPI is clock per instruction. What is CPI of this ARM processor? It's 0.5, right? So which means that this processor consumes 0.5 cycles per instruction, right? But if we see the real performance by benchmarks, then we can see that the real performance is about the about not 9 times. It's about the 18 times slower than the ideal performance, right? So you can say that even though this is this benchmark shows the highest performance, but even this benchmark shows the CPI of 0.97, which means that it's about 2x slower than the ideal performance. Okay, why? So you can find the pipeline stores. So why performance is degraded compared to the ideal performance? Because of pipeline stores. Right? So we did not learn about the memory systems yet. Also, you can find that performance degradation by memory hierarchy stores. So that is the wasted clock cycles by memory systems. So if you see just this benchmark, the performance of this benchmark is nearly 2x slower than the ideal performance, like because of pipeline stores, like the hazard. So that's why we need to reduce the hazard in the pipeline process, right? But also, another critical problem is memory system. So if you see that this benchmark MCF, so we can find that the wasted clock cycles by memory system is really high. Okay, so this is the ideal performance, but because of the slow memory system, then performance is nearly 16 times slower than the ideal performance, right? So it means in order to increase the performance of the processor of the system, we need to tackle the issues in processors, and also we need to tackle the issues in memory systems, right? So this result shows that, okay? Because we have memory systems now. Okay, so real architecture is also very, very complex. So I hope everyone has interest in this computer architecture. Okay. So I hope everyone can take the best courses in computer architecture. Okay. And then also I did not post the third lab assignment yet, but I will post the third lab assignment after this class. Okay, and then we will be requested to design a single cycle processor. Okay, but in the second lab assignment, you complete the design of data path elements. But actually, in chapter 4, we learned how to organize a processor. The first processor we learned in the chapter 4 is single cycle processor. So by organizing data path elements and then by using control unit, then we can build a single cycle processor first. And then we learned how to organize pipeline processor. So in the third level assignment, you will be requested to design single cycle processor, and then and actually in the second lab, so our AAU supports the additional instructions such as the exclusive OR, and then IPI instructions, and then some other instructions, like some other branch instructions. So our single cycle processor also needs to support additional instructions for this third lab. Okay. I will post the third lab assignment after this class. And then before moving on the memory system, let's talk about the simulation tools. So, okay, and then we'll discuss about the computer architecture simulation tools. Okay, so now, in this course, we are learning about some layers of computer systems, like actually this layer. Oh, okay, right. So we are learning about this layer, the architecture layer and the microarchitecture layer. So, when we perform research on this, not here, right, architecture layer and the microarchitecture layer. So when we perform research on this architectural layer, then what should we do? So which means that, and in chapter 4, we learned about the process architecture. And then we learned how, so actually the process architecture is changed from single cycle processor to the pipeline architecture in order to improve performance. So the research, so research on computer architecture focuses on actually two factors, like the performance and cost. So we need to improve the performance. Also, we need to reduce cost in the computer system or computer processor. So which means that we need to develop some very fancy ideas to improve the performance. Then how can we evaluate which means that the validity of our idea? So if we perform some researches on some research field, then we can develop some very new ideas or basic ideas. We can improve the performance or we can reduce the cost, but we need to evaluate our idea. Then how can we evaluate our ideas on the architectural field? Computer processor, for example. So the computer processor is very expensive. If we want to purchase the processor like core architecture processors, the price is about over 200 or maybe 500. But the processor is very expensive actually. And then, but another difficulty in this computer architecture research is that we cannot change the inside of the processor. Well, that's just a chip. And then, the main material in the chip is the SiO2, silicon dioxide, which means it's similar to the sand or rock. So stone, which means we cannot change the inside of a processor. Then how can we evaluate our ideas? So ideas in the architectural field just require to change the real architectures in a processor, like a single cycle pipeline processor, or some branch predictions, or also the out-of-order processing or speculation. How can we evaluate our idea? So we can work with real hardware actually. So like this device. So this device is an actual device I used in my research. If you see this device, you can find actually it's not clear enough this screen, but you can find this is actually the processor. Also, you can program this processor. So which means that this processor is actually called FPGA. So you can change the inside of this processor. We can implement some real design code, arcade design code, and then we can implement our idea inside of this FPGA chip. But it's not easy. So it means that we require this FPGA chip for this kind of research. But also this FPGA chip is very expensive. Also, if you use this board, this board is also very, very complex. And then, we can also change the connections inside of this board. So, which means we can change some architecture in this board, like in this chip, but this change is also limited because it's hardware, right? So it's not easy. It's not easy to debug. So if we just add some bugs in this hardware, it's very, very difficult to debug with this hardware. So actually, everyone likes software because software is just the software, so we can change everything in the software. And it's the same to the computer architecture field. So we can use software that emulates the behavior of processor. And then these tools are called simulators. Okay, so we can use architectural simulators to implement our ideas and to evaluate our ideas, processor architecture. Okay, so it's software, not hardware. What does that mean? Let's think about the 5-stage pipeline processor. So actually, in a lab assignment, you are designing the processor with the Verilog. It's a hardware description language. It's like a program language. But we can also make some software that emulate the behavior of 5-stage pipeline architecture. The Verilog is also the kind of programming language that describe the behavior of pipelines, like actually computer digital system, right? So which means we can also use some programming languages such as Python or C or C++ to implement the software simulator that emulates the behavior of processor. So these softwares are called architectural simulators. So it's software, even though the hardware behaviors are emulated. And then we can use these architectural simulators for our research. Okay. So, the RISC-V is a kind of brand new instruction set architecture. So actually, we are very familiar with Windows operating system that runs on the x86 processors. Also, we have someone familiar with the Mac operating system that runs on the x86 or ARM processors. Well, we are running about the RISC-V. It's a brand new instruction set architecture. So we are not familiar with the RISC-V. So first, we can use the assembly simulator. So actually, in chapter 2, we learned about the instruction sets in our RISC-V, which means we learned about the assembly codes for RISC-V assembly codes in RISC-V instruction set architecture. And then but problem is that our normal computers usually include x86 or ARM processors. So these processors cannot execute RISC-V assembly code, which means if we can estimate the result of the RISC-V instructions in a software, then we can execute the assembly code of RISC-V instructions. So assembly simulator of RISC-V support the execution of assembly codes in RISC-V ISA. So you can use the tools like this, like Jupyter, like 6. So also, Camera is the very popular tool. So actually, so I believe some of you already knows about the virtual machine, like the virtual box or parallels. I already posted that slide, so it doesn't catch it. So, but actually, the disadvantage of the virtual box is that virtual box only can run the operating system that supports the same instruction set architecture, right? Actually, the virtual box on an x86 processor only can run x86 operating systems. But Camera is different. Camera is also kind of a virtual machine, but Camera supports the different instruction set architecture. So which means that we can run RISC-V Camera on the x86 CPUs. Performance is very slow compared to the native virtual box or virtual machine. No, because the instruction sets are different. But with the Camera, we can run different kind of instruction sets on our host system. But if we want just to simulate the assembly code, then you can use the very simple tool like Jupyter. But Jupyter looks like this, so this is so small. Okay, so you can find the instructions here, and then is this a machine code? What is the address? This address is the program counter. No, the program counter is here, and also with the Jupyter, you can check the changes in the register file like here. So you can find the register number here like X0 to X31. So this is a different name of the X0, different name of X1, and you can find the potential in register file. And then also we can use the graphical architecture simulator. So this is the right. So this video is very familiar, right? I just captured this figure from right, and then also you can find the 5 stages of RISC-V processor in this right simulator. Okay, so this is also software. So which means that this right, I think that this right tool is a very good tool. So if you see some graphical behavior of how the instructions are fetched and decoded and then executed in every stage. Okay, so if we use right simulation tool, then we can easily figure out how instructions are fetched and how instructions are propagated to the next stage, and how instructions are executed, really executed, RISC-V process, this 5 stages RISC-V processor. And then this architecture is very similar to the 5-stage pipeline, the processor we learned in this course. So only difference is the location of the branch unit. So in our textbook, the branch is reserved just at the register 5, but in the right tool, the branch is reserved at the exploding unit. This is the only difference. So if you have difficulty understanding how the instructions are really executed and handled in a 5-stage pipeline processor. And you can install this write tool, and then you can run some example code. So you can write assembly code, so we already run some several RISC-V instructions in chapter 2, and then based on that technology, and you can write some very simple assembly code. And then assembly code has instructions, and every instruction can be given to this processor simulator, and then you can see how the instructions are handled in a real processor. Okay, so you can find right tool here. So I believe that you can execute this right simulator on your Windows or Linux machine or Mac operating system. Okay, it's a very good tool. Okay. So we have only 5 minutes, but let's quickly talk about the memory system. So I mentioned that the memory system is very critical for the performance of the processor because some performance example like benchmark, and you can find that the performance of a processor is degraded very much because of pipeline stored by memory system. So which means the memory system is very, very slow compared to the processor. So okay, use okay, so let's go back to this slide. So in chapter 4, we learned about the process architecture. So these are degraded performance by some issues in a process architecture. So as I explained, this is the ideal performance, but the performance is nearly 2x slower than when you consider the pipeline stores, like the hazard in a pipeline architecture. But for some benchmark, you can find that the performance is degraded very severely because of memory system. Because memory is very, very slow. Why memory is slow? So actually, you can find some memories in the process architecture. One memory, instruction memory, and data memory. But the performance, the latency of this instruction memory and data memory is just 1 clock. It's the same as the actually pipeline staging, the latency of the pipeline staging. But why the memory is slow? So actually, if we just want to purchase your computer systems, then we just check the size of main memory. Recently, the most of laptop includes the 8 GB of the main memory. So, but 8 GB. So this size is very, very large compared to the memory in the processor. So actually, the memory in the processor in chapter 4 is the cache. It's very small and very fast. But if the memory size is very large, the memory is very slow. So for example, if we use 8 GB of memory, the speed of this memory is extremely slow compared to the speed of processing. So which means that if the data is in the memory, it's the same. So actually, if the data is in the memory, then we need to use the load instruction. And using this load instruction, the data in the memory is transferred to the register file. But if the data is in the very large memory, the main memory, and then if we use the load instruction, this load instruction will take about hundreds to even thousands cycles to transfer data from main memory to the register file. It's because the memory is very, very slow. It said the register file is fast, so you assume that instruction memory and the data memory is memory is very fast, but actually the main memory is very, very slow. And then this instruction memory and then the memory size is very small compared to the main memory, because actually these memories are caches. So in chapter 5, we will learn about the memory systems or memory hierarchy. It's called the memory hierarchy. It looks like this. So this is the main memory. Main memory is here, but we are learning about the register file. Then later on cache I show you. So these memories are the register file and caches size is very small to very fast. But our all data is in the main memory. Okay, so which means that it's slow. So memory is very critical for the performance. In chapter 5, we will learn about the memory hierarchy of the computer system. This is also a very important part of the discourse. So please focus on that. Chapter 5. Okay. So I will stop here. Any questions? Thank you for your attention. Thank you for your effort in this course. Please enjoy the better. Thank you guys.